So we will start with the definition of a limit. The definition of a limit, and this isn't a super formal definition, but I think one that's easy to understand. And it's what a limit is. It is a y value, a function approaches as the x value gets infinitely close to a certain point. So that is the definition of a limit, and I'm going to add some notes in a second. But it is a y value. It is a y value a function approaches as the x value gets infinitely close to a certain point. And so I'm going to change this to the y value. I'm going to underline some words that I think are the most important when it comes to what a limit is. So one, a limit is always a y value. So if you're looking at a graph and you're trying to determine what a limit is, you have to use the x value to find it, but you should always be writing down the y value, not the x value. Approaches is a really important word because the function just has to approach it. It doesn't actually ever have to hit it. And so that brings me to my little note right here, is that a function can but doesn't have to hit the y value. Doesn't have to reach that y value. And I'll talk about that more in a second. But whatever the limit is, it doesn't actually have to reach it. It just has to approach it. And then infinitely close, I think, is another word, because that's just all of what a limit is you're getting really, really, really close to something. And so here's my first example over here. If you look at this graph, say we want to find the limit at x equals 1. So basically what that means is we want to figure out what y value at x equals 1 does the function approach as the function gets infinitely closer to 1. And so as I approach, so here's my x equals 1 right here. As I approach, I'm getting really, really, really close to 4. And so the answer is 4. But if you notice, there's a hole in the graph at 4. That does not matter. That doesn't change the limit. What that means is that f of 1, it doesn't equal 4. F of 1 equals 2 instead, because that is where there's a filled-in point. But the limit and the point are two different things. And so just because a point isn't there doesn't mean a limit doesn't exist, because limit is all about approaching and the idea of being infinitely close. It doesn't matter about what the actual point is. So I guess I wrote that here too. A limit can exist even if a point doesn't exist. And so now we're going to talk a little bit about limit notation and how to say it. So I'm going to fill in some of these things on my graph, but they should already be on your printed handout. So first, this is just standard limit notation. You will always have things filled in for C, and then a lot of times it will be your job to find R. But here's an example of how you say this. And if you're at home or if you're in class, I would encourage you to practice saying this out loud so that you can have the correct academic language. So how I would say this is the limit as x approaches C of f of x equals, you could also say is R. So the limit as x approaches C of f of x equals / is R. And so here are some examples. First, we have the limit as x approaches 3 of g of x. And we are told that that equals 1. So if you want to try to practice writing that out, you're welcome to. I'll kind of write it right here. But the limit as x approaches 3 of g of x is 1. And let's look at the graph just to get that down a little bit more. So if we look at 3 here, that's where 3 is. And as I approach 3, look where my graph goes. The function approaches 1, because if you look, these are kind of skip counting on the vertical and horizontal axes. So it's 1. Another example, and this one I think is important, is the limit as x approaches -1 of h of x is 2. And if you look at this graph over here, this is an example where the point and the limit are actually the same thing. So if you go to -1 and you approach -1 from the left and from the right, you get hit at 2, but also that point is filled in, so f of -1 is also 2. So sometimes the point and the limit are the exact same thing. And so the way that you would write this out, if you want to practice, is the limit as x approaches -1 of h of x is 2. And notice that I went from using the g of x function to the h of x function, so I switched those. Just so you know, I'm not going to pause throughout this video because you can just use that. So if you need to pause, feel free to pause, replay anything. And so here are just some other examples of limits graphically. So this one says the limit as x approaches 0 of f of x is 0. So as I approach this one, if you look, it's going to 0. This one's kind of an interesting, I'm going to add some arrows on this function right here. This is a rational function, and rational functions tend to have vertical asymptotes. And so because of that, so if you look right here, like you can tell that as this function gets closer to -3, that it's continuing to kind of like that gap is getting smaller. Those lines are getting closer, but there is a vertical asymptote there. And so they're never actually going to cross. And so rational functions tend to have a limit that is infinity or does not exist or negative infinity. And we'll get more to that in a second. But if you look as we approach from the left, as we approach from the right, this function is just getting infinitely higher. And so as it approaches -3, it's going to get closer and closer to infinity. And we'll talk more about the infinity limits in a second. This is the same one, so I'm just going to skip it. And then for this one, this function right here, it says that the limit as x approaches 0 doesn't exist. So as it approaches 0, so this is 0, right? It doesn't exist. So I want you to pause and think, why do we think that this function doesn't exist? Why do we think this limit doesn't exist? And so maybe you're noticing the problem. As I approach from the left of this function to get to 0, and as I approach from the right of this function to get to 0, well, when I approach from the left, my y value is 1. But as if I approach from the right, my y value is 0. And this is called a piecewise function. And so this is something you have to look out for a lot in piecewise functions. But this does not exist because my left-hand limit and my right-hand limit are not the same thing. And if those are not the same thing, then the limit doesn't exist. And so I hope you guys got that. It's okay if you didn't. But on the next page, we're going to go through the 3 reasons why a limit might not exist. So, and we've kind of seen some examples of 2 of these already. The first one is exactly what we just said. The left-hand limit and the left-hand limit does not, sorry, that's not a lot of space, does not equal the right-hand limit. So that's the first one. The second one is the limit isn't a finite number. And so if you can't remember what finite means, it just means it's like actually a number. It's not imaginary. It actually exists. So like 4, 1,000, 2/3, -2,300,000. Those are finite numbers. And so sometimes the limit isn't going to approach anything finite. For example, it might go to infinity. And so infinity technically means the limit doesn't exist, but we don't usually write do not exist if it's infinity, just so we can be specific with why it doesn't exist. So I wrote here, technically, if a limit goes to infinity, it doesn't exist because it goes on forever. It never reaches a finite number. However, we normally describe it as infinity or negative infinity because it's a more specific reason to explain what is happening to a function. And then the last one, this is probably a word that you haven't heard before, and I'll show you an example again of this in a second. It says the function is oscillating. Oscillating. And I will show you what that means in a second. So here's our first reason. So this is our number 1 reason why a limit wouldn't exist. So we have like a little bit of a new part of our notation. If you guys didn't notice, we are working with the limit involving 1. But on this first one, there's a negative. And then on the second one, there's a plus. And so what does that mean? Well, if you ever see that symbol on the right side of the number, so it wouldn't, like this, that's normal, right? That's just -1. But if you see it on the right side of the number, that means you're either working with a left hand or a right hand limit. So this negative means that you're working with a left hand limit. So this means from the left, and that's always a minus. And then this means you're working with a right hand limit. So the way that I would say this limit is the limit as x approaches 1 from the left of g of x is. And so let's look at our graph. We'll find 1. So 1 is right here. And I'm going to approach 1 from the left. So I'm going to come from this direction. And as I approach 1 from the left, where does my y value go? What are we getting infinitely close to? The answer is 4. If you guys want to try the right one by yourself, feel free to pause. But as I approach from the right, I'm getting infinitely close to the y value, -2. And so because of that, and yours has this right here, because that those are not the same thing, that means our limit does not exist. Our limit does not exist because I'm going to write this in notation, and I encourage you guys to practice this because notation is so important in calculus. It helps us be accurate, and it saves us a lot of time to not like write things out in words. And so how I'll write that is the limit as x approaches 1 from the left of g of x does not equal the limit as x approaches 1 from the right of g of x. Those are not the same thing because 4 and -2 aren't the same thing. So this is our number one reason why a limit might not exist, and this is honestly one of the most popular reasons that you'll see. Example 2 is our example of an infinite limit. So this is kind of similar to the one we saw earlier, but let's say we're trying to find the limit as x approaches 0 of f of x, and this is the function f of x. Well, if you look, it seems like they are approaching the same thing, but if you approach from the left, it's going, this function is going down forever, and it's going rapidly, and then as you approach from the right, it's also going down forever rapidly. And so if it's going down instead of up, so if it's approaching the negative y values instead of the positive y values, the answer is going to be -infinity. And so this technically does not exist, but the reason it doesn't exist is because it's approaching -infinity. And our last case is our oscillating example. So this is oscillating. And if you look, as we approach 0, it seems like this function can't really make up its mind. And so it's a little hard to see here, but if I go to desmos.com, and as you zoom in, you can kind of see more that this function is going up, down, up, down, up, down. It's actually switching between the y value 1 and the y value -1. And I can't zoom in anymore, but, oh, I guess I can. But if you look at that, like that hurts your brain, but it's just going up and down forever. And so because it's never coming to one single point, its limit doesn't exist, and it doesn't exist because it's oscillating. So most of the functions that do that are going to be trigonometric. I think most, maybe all, are going to be trigonometric functions. So we're just going to do a couple example problems here. Sorry, sometimes when I send to Notability, things don't copy over, but you guys are welcome to kind of start answering these questions as I write. X approaches 6 from the right, f of x equals 3, and the limit as x approaches 6. Okay, sorry. So the first question here asks us what is, oh, sorry, I typed in all those answers as I wrote down. Pretend you don't know them. The first one asks us what is f of 6. This is an Algebra 1 question. There's nothing new about this. It's just saying what is the output when the input is 6. So I'm going to find 6. And I'm looking for a filled in point, like an actual point. This right here is not a point. That means there's a hole in the function right there. But if you look, there's a solid point here, and that y value is 4. So f of 6 is 4. Now I want to find the limit, the left-hand limit. So the limit as x approaches 6 from the left. So I'm going to find 6 again, and I'm going to approach it using the function, and I'm going to approach from the left. And there's no function part attached to that solid point, and so I just like ignore that when I'm using the limit. It doesn't matter. But as I approach from the left, I'm going to hit the y value 3. As I approach from the right, I'm also going to hit the y value 3. So that means this limit as a whole does exist, and it is 3. So going on to the next one. Same thing, I'm going to write these down. Okay, so first we have f of 2. So if I go to find 2, well, when I look at 2, there is 1, there's a hole here, and then there is a dotted line, which indicates that there's a vertical asymptote, which means that the function is never going to touch across the line, which means that there's no point here. So f of 2 does not exist, so this is not a point. However, just because there's not a point doesn't mean there's not a limit. So I'm going to find the limit as x approaches 2 from the left of f of x. So if I come from the left, this is going down forever, which means that as we get closer to 2 from the left, our function's approaching negative infinity. And then as I approach 2 from the right, I'm getting closer and closer, infinitely close to 4. It's okay that there's a hole there. The function is still approaching that. And then because those two things aren't the same thing, we're going to put does not exist. Last one, this is the last one we're going to do. Some of these questions are a little tricky, and I put them in there for a reason. So first, question number 1 says f of negative infinity. That is asking for what is the y value when the input is negative infinity. And negative infinity just doesn't, that doesn't exist. It's not a point. And so this is just an example of a bad question that doesn't really make sense. And so this is an example of a question you would not get on an AP test. It is hard. But it also doesn't make sense. And so you're going to get hard problems on AP tests and throughout this class, but they're going to make sense. Same thing with this next one. So we're going to look at these one at a time. The limit as x approaches negative infinity from the negative side. That also doesn't make sense because negative infinity is going to the left forever. So you can't really approach it from the negative side. So this was another example that doesn't, it's a bad question. So I'm canceling it out. Then we have the limit as negative infinity limit as x approaches negative infinity from the right side. So that is the first example that actually does make sense. That just means we're going to approach negative infinity from the right. So we're going to go to the left forever. And if you look at that asymptote, this is a horizontal one. It looks like this function is getting closer and closer to 3. So it's approaching 3. And then this one doesn't have the plus sign on it, but it really is just asking the same thing. As we approach negative infinity, where is the function going? And because of that horizontal asymptote right there, we know it's going to 3. So that's the first set. And feel free to pause and try these without me. F of negative 7, so this is where negative 7 is right here, is as you see, there is no point there. There is a vertical asymptote, so this does not exist. But as you approach from the left, it's going to negative infinity, and so also the same thing if you're approaching from the right. And so the limit as a whole is negative infinity, because the same thing happens from the left and the right. Now we'll go to f of 0. F of 0, there is a solid point right here. So the input when the output when the input is 0 is 1. As you approach as you approach 0 from the left, you get 1. As you approach 0 from the right, you also get 1. So that limit does exist, and it's 1. And then our final one for the day is f of 3. So as I find f of 3, I use the point, and that is 4. As I approach 3 from the left, I go to 4. As I approach 3 from the right, I go to 5, and so the limit doesn't exist. And that is our notes for the day. So that's it. Thank you guys for listening. Feel free to write down any questions you have for me and email me them, or I will give you an opportunity to ask them in class tomorrow. Thanks.